Hello, my name is Kosi. This is milestone 2 of my final year project. In milestone 1, last time I compared Reno. I compared just Reno and CUBIC. So now I've added the BBR as Google's bandwidth bottleneck round trip propagation time. Name is just weird to me too. So there are now four algorithms, actually three, but I added a second cubic flow so that there will be four senders that are just fighting for the same 10 Mbps bottleneck. I also tracked the queue size live, so I'm just going to show you what's happened. Because I'm going to go to my code. Here, this is the topology. Like I said, four senders: Reno, CUBIC, BBR, and another CUBIC. Just because why not? That's the four senders. Then the senders creates for. This is where I set them to the particular algorithm they are going to use. This one is TCP new Reno. Hold on, this is I'm using ns-3. ns-3 network simulator 3. So here I'm using the Reno algorithm. I'm using CUBIC, here I'm using BBR, and here I'm using CUBIC again. I don't know why I'm yawning. Oh. Also, there's the Q traceback I talked about. Also that's in line, but yeah. Okay, so I'm just going to go straight to my results. Because I'm going to show the throughputs. Yeah, the throughputs. Well, here's the throughput on flow 1 Reno, got about 2.28 Mbps, while flow 2 got 2745, that's 2.745 Mbps. This one got 2045. Just to be clear, this is CUBIC, this is Reno, this is BBR. I think I zoomed in too much. How do I zoom out? Just gonna close it and open it again. And I forgot how to zoom out. Silly me. Okay. I'm started again. Flow 1 Reno got about 2.2728, approximately 28 Mbps. Flow 2 CUBIC got about 2.74 Mbps. Flow 3 got about 2.05 Mbps. Flow 3 is BBR, the new one I added, and this one flow 4 at about 2.88 Mbps. Okay, so adding them up, that's about 9.95 Mbps. Well, that means that the bottleneck link is completely saturated. Exactly what I expected from 10 Mbps pipe, because the pipe is just 10 Mbps, so that's basically what I expected. But if you notice here, this BBR, the new one I added, it got the list, even though it tries to be smart, because the two CUBIC flows here, they drop the most because they are extremely aggressive. Not just how CUBIC is very aggressive. They push their window up faster, harder than Reno first flow, and they overwhelm these guys' space in BBR. So I'm just going to go to the next image. The delay. We're talking about delay now. Delay. The three of them, they are loss-based flows. They have about 62, 59, 60. These three of them, as flow, flow 1, Reno, cubic, and this other guy there, still cubic, they have about 60 milliseconds of delay, but BBR is up there at 82. Why? Well, that's because the cubic flow here, it still fills the queue to its 100 packet limit most of the time, while BBR tries to probe for more bandwidth. Its packet will just kind of to arrive right when the queue is already full, so they will sit there longer and to end up suffering from everyone else's buffer floats. Yet, but if it's only BBR in the network, then this won't be a problem. But in an ideal network, different algorithms competing for the same bandwidth. That's the whole point. So, just going to go on to the loss. I've seen this before. Well, the packet loss basically tells the same story here because Reno and CUBIC here. No, this is Reno, this is CUBIC, this is also CUBIC, this is BBR. Reno and CUBIC, they lost less than 0.2%. It's not exactly 0.2%, but yeah, you get the points. BBR lost over 2.5%. That's about 10 times more. Over 10 times more. Well, again, because the queue is constantly full. As I said before, it's constantly full. So BBR's its probing will just to get dropped instantly. It's really a harsh environment with model-based algorithm like BBR. BBR is model-based. So now I'm just going to go to the fairness. I think that I just remember. James fairness index came out to 0.98, very close to 1, which means it's almost perfectly fair. This might surprise you here because CUBIC got 30% more throughput than BBR, but fairness is not exactly about tiny differences. It's about whether anyone is starring. All four flows, as in the four of them, this is actually 3. One is just an extra cubic. All four flows here, they are in the range of 2 to 2.9 Mbps. So mathematically, that's fair. The problem here is this fairness came at cost of high delay and unnecessary loss. It's still kind of brute force. It's a brute force kind of fairness and it's not exactly smart. Now to the queue occupancy. Well, this is like the most important chart of like all of them. It shows the number of packets sitting in the bottleneck queue. Bottleneck queue occupancy every time. Okay. This just shows the amount of packets that are sitting in the bottleneck queue over the 60-second simulation. The simulation ran for 60 seconds. So if you look at that shape, it's like a sawtooth, if you might say, like sawtooth, like the tooth of a saw. What's happening is basically the classic TCP AIMD cycle. The senders slowly increase their window. The queue fills up. At 100 packets here, the queue is full and the router will drop to the next packet. Then the sender detects that loss and they half their speed. Then the queue will become empty. Then they start ramping up again over and over. That's just the buffer floats in action. The queue I configured here, is just about, it's just 100 packets. but the actual bandwidth delay product of this thing is only about 18 packets. That's how many packets can be in flight without causing a queue. Without causing, you know what the queue is now. I don't have to explain that to you. So I've created a queue that's 6 times larger than needed. And the loss based algorithm, they're perfectly happy to feel it obviously now, because the queue I created is 6 times larger than what's needed, 18 packets. That's why the delay is high, obviously. Now, what does this mean, or why does it matter for my project? I wrote an observations file, but because I'm a reinforcement learning based congestion controller, it should be able to smooth out this sawtooth. Be able to smooth it out. So now imagine my multi-agent reinforcement learning agent they will learn to keep that queue at say 20-30 packets instead of bouncing between 0 and 100. So basically they could still achieve near that 10 Mbps throughput because the bottleneck is being fully used when it's it's adjust between, let's say, 20-30 packets. Yeah, so that's the goal. Smart fairness and not just brute force fairness. It's much lower delay. It will just drop down from maybe about 60 ms to 30 ms, and then there's almost 0 packet. If everything goes planned, 0 packet loss. That's the goal. Okay. Well, all the code and results and graphs are in my repository. Milestone 2 done. Now moving on to milestone 3, single agent RL. Before I then move on to MARL. Milestone 1 was network samples in my previous video. This one is just congestion dynamics. Milestone 1 added the only 2 flows there, Reno and CUBIC. Now we have Reno, CUBIC, BBR. Said BBR before is Google's Bottleneck, bandwidth, round trip. Well, round trip, yeah, propagation time. That name still mind boggling. So makes sense though. Still, I think that's all for this video. See you all in Milestone 3.